Okay, so I'm going to go over the problems in our first exam. So starting off with number 1, the catheter problem. This may be hard to read, so just refer to your exam question. But the first thing that it asks us to do is find the momentum balance to derive the governing equation. So to do that, we're going to first need to set up our control volume. And if you remember, in cylindrical coordinates, it's going to be kind of like a donut shape. So this is our control volume right here. It's going to have, it's just this portion that we're going to be looking at all the way around here, and it's going to have some length, delta Z. So you can think about it as it is positioned at some radius, little r, from the center, and it has a thickness of delta r is our donut, and again the length is delta Z. Here is our catheter, which is a solid, and so again what's happening is the fluid is moving all around this catheter. And we look at the pressure gradient due to from the blood flow. It's going to be acting on this surface right here, and so that is going to be delta R times 2 pi r, which is going to go all the way around here. So that is the surface that the pressure is acting on at Z, and then the opposite direction at Z plus delta Z. The shear stress is acting on the inside wall in this direction at R, so this inside wall right here all the way around, and then at R plus delta R, it's going to be acting on this outside wall in this direction. And so these walls right here that it's actually acting on, we can see it to be, it's going to be delta Z times either R plus delta R for this, or R for this inner part. Is that right? And then 2 pi for the whole, for the circumference. So for our balance, we can start off with the sum of forces equals the net momentum transport. So if we look at our sum of forces, again the sum of forces are our pressures and our shear stresses. So those are our two stresses or forces. It's going to be P, the pressure at Z, this direction, minus the pressure occurring over here on this direction, again times 2 pi r delta r, so that's just that face that it's acting on right here, this one and the same one on the opposite side, plus your shear stresses. So again, the shear stress on this inner wall and this outer wall. So on the outer wall, it's the shear stress at r plus delta r times that radius right here, which is r plus delta r, minus the shear stress at the inner wall times the radius, and all that's multiplied times 2 pi delta Z. And then that indicates the sum of forces. And now what is the net momentum transport? The net momentum transport is given by this equation. And this is the net momentum that's moving in into here and out this other side. So it's acting again on the same face that your pressure is acting on. But what we know is that Vz is only dependent upon R. So Vz at Z plus delta Z and Vz at Z are the same things. And we know that rho is constant. Our densities are constant. So this term right here and this term right here are exactly the same. So they're going to cancel one another out. And so there's going to be 0 net momentum change. So it's going to end up being the sum of forces equals 0. So this part is equal to 0. So if we take our our balance and divide by the control volume, which is 2 pi r delta z, we get this for our equation. You can see I just went ahead and moved the shear stresses over to the other side of the equation. When you divide it out, this is what you're going to have. And you take the limits as z and r go to 0, and you have your governing equation, which is dp over dz equals 1 over r times dr tau rz divided by dr. So that's the governing equation that I was looking for, that describes the fluid motion in the blood vessel. And actually this is with or without the catheter, because this is just going to be for any kind of cylindrical geometry.